Uh, Good evening, everyone. Today we are going to present our topic on performance analysis of SSTF disk scheduling algorithm. I am Preksha Bhandari, and along with my partner Nitik Agarwal, we will be explaining how SSTF works, its performance advantages, and comparison with other algorithms. Introduction. Let's begin with the introduction. Disk scheduling is an important concept in operating systems. It is used to decide the order in which disk reads and writes requests are processed. The main goal of disk scheduling is to reduce seek time, which is the time taken by the disk head to move from one track to another. By optimizing this movement, we can significantly improve overall system performance. Efficient disk scheduling also ensures better utilization of hardware resources and faster response time for users. Now let's understand the basic concept of disk scheduling. In a system, multiple disk requests are generated at the same time. The operating system is responsible for deciding which request should be served first. The objective is to minimize the total movement of the disk head, which directly affects performance. Efficient scheduling helps in handling multiple requests smoothly and ensures that the system works faster and more efficiently. What is SSTF? SSTF stands for Shortest Seek Time First. In this algorithm, the request which is closest to the current position of the disk head is selected first. This means the algorithm always chooses the request with the minimum distance from the current head position. Because of this greedy approach, SSTF reduces the total seek time and improves performance compared to simpler algorithms like FCFS. However, since it is always since it always prefers the nearest request, some far away requests may get delayed.
I will explain the working of SSTF algorithm step by step. Here the first step that we have is we take an array of disk requests and the initial head position from the user. Then we calculate the distance between the current head position and all the pending requests. Next, we select the request which has the minimum distance from the head. This request is then serviced and the head moves to that position. Then we update the total seek count and repeat the same process until all requests are completed. This step-by-step approach ensures that the head always moves in the shortest possible distance. This is the implementation of the code of SSTF. Over here, as you can see, first we've defined SSTF as a function, and then we are finding out using a while loop, we are finding out the closest request to the compared to the head. And then we are using append and remove to allocate the head to the processes and everything. After which we are taking the user input as the number of disk required, what is the disk values with a space to separate them, then initial head position. After which then we run the SSTF function, and then we have the output that basically prints the SSTF disk scheduling and the sequence and the total seek time that we get. Over here is the example that we took. As you can see in the queue, there's 98, 183, 37, 122, 14, 124, 65, 67. And the initial head is 53. So when we put this input as a user in the code, the sequence that we get as the shortest part would be 65, 67, 37, 14, 98, 122, 124, and 183. And the total seek time for SSTF would be 236. Comparison of SSTF with the other different algorithms for disk scheduling, that is FCFS, post come post serve, scan, and look. In FCFS, requests are processed in the order that they arrive, that is post come post serve. It is simple but results in high seek time. As you can see, the highest seek time in the graph shown is of FCFS, that is 640. It is simple to implement, but it has very poor performance because of the seek time. SSTF gives the lowest seek time. It is the most efficient, but it may cause starvation. Scan works like an elevator and provides better fairness compared to SSTF. It has a little more seek time compared to SSTF. And then moving on to look. Look is an improved version of scan and avoids unnecessary movements. It also has balanced performance, and seek time is 299 compared to SSTF. Look is better than scan. As I mentioned, it's an improved version of scan. That's why. According to the research, SSTF significantly reduces average seek time compared to FCFS. It is often used in combination with other algorithms to improve performance. However, improvements are needed to solve the starvation problem. This makes SSTF a good base algorithm, but not a perfect standalone solution.
Now let's look at the advantages of SSTS. It is faster than FCFS and significantly reduces seek time. It improves system throughout and provides quicker response time. Because of its efficiency, it is widely used in disk scheduling systems. However, SSTF also has some disadvantages. The biggest issue is starvation, where some requests may never get served if they are far away. It is also not suitable for time-critical systems where fairness is important. So while it is efficient, it is not always reliable in every situation.
Research insights. So after studying the single research paper, we've referenced it in the PPT. This is what conclusion we've come on to from the research, that SSTF significantly reduces the average seek time compared to each and every algorithm that we've mentioned in the presentation. It is often used in hybrid algorithm, that is by combining other algorithms to improve performance. It performs better than FCFS in most cases. However, as mentioned in the disadvantages, it requires improvements to handle starvation, as that is one of the major problems in SSTF algorithms. So in conclusion, SSTF is a good base algorithm, but not a perfect standalone solution. Moving on to the conclusion, SSTF is an efficient disk scheduling algorithm that minimizes seek time and improves performance. However, it is not perfect, again, due to fairness issues and starvation issues. With proper improvements, it can be used effectively in modern systems. It is also one important part of operating system concept, and this is the reference that we've taken: analysis of traditional disk scheduling algorithms. A review. We found this paper on the review websites. Thank you. We'll end our presentation.